cosines. Prior to these video notes, these are the video notes for Objective 8, Law of Sines and Cosines. Previous to this, we have used sine, cosine, and tangent to solve right triangles, which we called right triangle trigonometry. Now we need to take right triangle trigonometry and extend it to non-right triangles. So let's take a look at an oblique triangle. We'll label it alpha, beta, gamma, A, B, C. We can't use SOHCAHTOA. We can't use sine, cosine, or tangent because this example does not have a hypotenuse, which means the opposite over hypotenuse does not apply. What's happened is that we want to take what we know about right triangles and extend it to non-right. So to create the law of sines and law of cosines, mathematicians took our non-right triangles, divided them into right triangles with a hypotenuse, and found that you can still create a relationship between all of the sides. For example, sine of beta is equal to h over c, but sine gamma is equal to h over b. Well, since both of these equations are equal to b, or equal to h, we can show, oh, why am I writing so crooked? We can show that b sine gamma is equal to c sine beta, or that sine gamma over c is equal to sine beta over b. This is the origin of the law of sines. Imagine that we continue to do that for alpha as well, and you would find that the sine of an angle over its side is proportionate for all three angles in a non-right triangle. So the law of sines states that sine alpha over A is equal to sine beta over B is equal to sine gamma over C. And so for our class, while we're not actually going to derive the law of sines, which you saw me do in the non-right triangle, we're going to apply the law of sines to solve two specific cases of triangle given information. Let's take a look at that in our next example. So the law of sines is mainly useful when we are given two angles and a side. If you remember from triangle proofs back in geometry, you know that you can prove two triangles are congruent if an angle, side, angle are congruent, or if an angle, angle, side is congruent. These are two examples of given information where the law of sines would work. Now, in geometry, as we're doing triangle proofs, we learned that you cannot prove two triangles are congruent if they have a side-side angle congruent. We also learn in geometry, as we're doing triangular congruent proofs, that you cannot prove two triangles are congruent if you have side-side angle. We'll see, however, in this video that you can use the law of sines to solve the triangle. So let's take a look at a couple of examples with various given information that allows us to use the law of sines to solve. For our first example, we're going to take a look at a triangle where alpha is 28 degrees, beta is 66 degrees, and side C is 8.2. So as I'm solving, I like to give myself a model, so I tend to draw an equilateral triangle and label the three angles and three sides. Then I need to take my given information and go ahead and fill it into the triangle. So I was given that this angle is 28 degrees, this angle is 66 degrees, and this side is 8.2. Well, my goal with solving a triangle is to find all missing sides and angles. So the first thing I see right away is that I can find the third side by using the triangle angle sum of 180 degrees. Since I know that all three sides of a triangle add up to 180, I just need to say that gamma is equal to 180 minus 28 plus 66 degrees. And we find that gamma is 86 degrees. Next, we're going to use the law of sines to find the missing sides. So if you recall, in the last segment of the video, we wrote down the law of sines. And the law of sines basically hinges on you knowing one angle and its corresponding side. So if we go back to the information we have, we know one angle, gamma, and its corresponding side, c, and we can use it to find the remaining corresponding sides. So we'll be using this portion of the law of sines, and then we'll be using the sine A equals sine C portion. Let's start with B since they're adjacent. We're going to write that the sine of 66 degrees over the unknown side B is equal to the sine of 86 degrees over 8.2. If we cross multiply, we get B times sine 86 is equal to 8.2 sine 66. Then we divide both sides by sine of 86, and make sure your calculator mode is in degrees because these angles are given to us in degrees. We find that B is approximately 7.5. I like to do a logic check. I know that gamma was the largest angle at 86, so C should be the largest side. My answer for B is not larger than my answer for C, so I'm happy that it fits via the hinge theorem. The next angle I'm going to find, or side I'm going to find, is A. So I'm going to set up the same proportion, but this time I'm going to say sine of alpha over A is equal to sine of 86 over 8.2. And this time I expect to see an even smaller answer than I got for B because alpha is the smallest angle in the triangle. Cross multiplication gives me a similar equation that it did last time. And this time when I use my calculator, since only one value in my proportion has changed, the 28 degrees, I'm going to use my calculator and just hit second enter. And I'm just going to change from 66 degrees to 28 degrees. And I find that alpha is approximately 3.9. Alpha A is approximately 3.9. And with that, I have used the law of sines to solve a non-right triangle. At this point, it's important to take a look at triangle relationships that use the side-side angle, which is two adjacent sides and the angle that is not in between them. Let's imagine that we know angle A is alpha, and we know that side next to it, B, and then we know the length of the next side. So the problem is we don't know the angle that this side hinges off of. We only know the length of this side. That means that there's multiple options for this length. For example, if this side is too short, like I've drawn it in my picture, you could conclude that no triangle is formed. If this triangle is the length of the hypotenuse, you can see that one right triangle would be formed. If this side is not exactly the hypotenuse, but is not extended very long, you can actually form more than one triangle. So let's draw in a hypotenuse. And then what you would see is that you have a possibility here and a possibility here that both rely on the same side length. So you'd actually have two possible solutions. The last case is if this side is long enough, then rather than having two solutions, I would actually have only one solution for the triangle. So because in side, side, angle. You know one angle. You don't know this angle. You can't predict, or you can't guarantee that you have exactly one triangle until you know the length of that second side and solve. So let's do one example for the notes where we solve with the law of sines and get two triangles as a result. And I'll leave getting exactly one triangle, which would look just like our first example, and I'll leave getting no triangles for in class or during homework assignments. So given beta is equal to 56.3 degrees, A is equal to 8.3, and B is equal to 7.6, we need to solve the triangle. Again, I like to draw an equilateral as my base diagram and then fill it in with the given information. So alpha, beta, gamma, I know 8.3, I know 7.6, and I know 56.3 degrees. Unlike in the last example, I do not know two of the angles, so I can't find the third angle. However, I do know an angle and its corresponding side, which is the kind of setup I'm looking for to use the law of sines. So I can see that I'm going to be starting with sine beta over B is equal to, and since I know A, I'll be using sine A over A, and I'm going to start by finding the missing angle A. Cross multiply from here, you get 7.6 sine A is equal to 8.3 sine 56.3. Divide both sides by 7.6. And using your calculator, you get that sine A is approximately 0.909. Now, I'm not going to leave that answer rounded when I type it in my calculator. I'm going to use its full value that's been stored. As you can see, we don't actually know what angle A is. We know what sine of angle A is, and so we're going to be using our inverse functions. A is equal to the inverse sine of 0.909. And like I mentioned, I'm not actually going to use 0.909. I'm going to use the answer stored in my calculator. So I'm going to do inverse sine of answer. And I find that A is approximately 65.3 degrees. Since my first angle was rounded to the nearest tenth, I'm going to leave this answer rounded to the nearest tenth as well. Now this is where the ambiguous case comes into play, because there are two angles less than 180 degrees that have a sine of 0.909. We saw this in the last objective when we were learning about inverse trigonometry. And so we need to find both angles from 0 to 180. So this is the first answer. And if we take a look at a diagram of the four quadrants, sine being 0.909 is about right here. Where is the other angle on the unit circle that would have the same sine value as this one? It's right here. So to find this mystery angle, we need to do 180 degrees minus 65.3. And we get 114.7 degrees. So we have to pay attention to the ambiguous case if it's possible for both of these answers to form a triangle following the 180 degree angle sum rule. I'm going to go ahead and erase this work here. And we're going to start setting up our answer to represent the idea that there are two potential solutions. And so I have my first solution for alpha, beta, gamma, and I have my second solution for alpha, beta, and gamma. And in my first solution, I know that alpha is 65.3 and that beta is 56.3. And so the missing angle gamma would be 180 minus the sum of those two angles, which is 58.4 degrees. Then my second solution, I know that alpha is 114.7 degrees. I know that beta, again, is 56.3 degrees. And that gamma is 180 minus the sum of those two angles. And so we find that gamma is equal to exactly 9 degrees. These are two potential solutions that would have two different values for side C based on the size of angle C. So let's find side C now that we have the two different setups. Again, remember that alpha has been rounded, so we want to use beta and B to find our missing side. We're going to say sine of 56.3 degrees over 7.6 is equal to sine of 58.4 degrees over C. We'll set up the same equation using our other value of C. And we'll solve both of them using cross multiplication. C sine 56.3 is equal to 7.6 sine of 58.4 divide by sine 56.3. And we get our first answer for C is that C is approximately 7.8. Does that fit within our triangle? We know that alpha is the largest side and largest angle. We now have gamma is the middle side and middle angle, and beta is the smallest side and smallest angle. Everything shakes out the way that it should. Solve the same equation over here. C is equal to 7.6 sine of 114.7 divided by sine of 56.3. And you get that C on this alternate triangle is approximately 8.3. And so we have successfully solved the triangle with both potential solutions. This is going to conclude the video notes for the law of sines. In the next half of the video notes, we're going to use the law of cosines to solve triangles with other given sets of information.